Hello everyone. We present our new proposal, a divide and conquer C++ parallel skeleton library focused especially on unbalanced additive problems for distributed memory environments. Parallel programming in distributed environments is still a complex task for the programmer today. Over the years, a variety of automatic solutions have been created that attempt to solve this problem. However, the solutions frequently have some drawbacks, such as considerable sacrifice of performance in favor of programmability, and, in many cases, the lack of some dynamic load balancing system. Without this, unbalanced algorithms are very difficult to parallelize by these solutions. Due to this downsides, most current HPC programs continue to use low-level libraries, such as MPI and OpenMP, for example. As a proposal to this problem, we present a new skeleton in the form of a header-only library for C++ that allows automatic parallelization of parallel problems in distributed environments in efficient and scalable way. The skeleton instructs the user about everything related to parallelization, such as managing the distribution of tasks, for example. Instead, the user only has to worry about relating his problem into the interface provided by the skeleton. Internally, the skeleton implements a dynamic load balancing system specially adapted to deal with deep and unbalanced problems. This skeleton is oriented to solve divide and conquer problems, which is a pattern applicable to many problems. It can even be used to implement problems that don't naturally fit into this pattern, such as map-reduce problems, for example. A divide and conquer algorithm is one in which a problem can be divided into several subproblems of the same type, and these child subproblems can also be divided into more subproblems, and so recursively, until we arrive at a base case that gives us its individual solution. We then recombine these individual solutions to arrive at the final result. An example is the recursive calculation of the Fibonacci number. There are more efficient algorithms to calculate it, but it's a widely used example because it easily shows the structure of a divide and conquer algorithm. The Fibonacci number of a number n is defined as the sum of the Fibonacci number of n minus 2 plus n minus 1, as we can see it in this example, where this problem division is done until we reach the base case, that are solved directly. Base cases are those in which n is less than 2. Our skeleton, called the parallel stack recursion, relies on efficient cork stealing techniques to implement a dynamic load balancing systems. For this, it combines the use of a shared memory techniques such as C++11 threads and its synchronization directives with distributed memory techniques, where MPI calls will be used to communicate the process and perform the steps. For shared memory, we inherit the techniques used in parallel stack recursion, a skeleton similar to this, but oriented only to shared memory systems. To allow the transmission of objects through MPI, our library uses the well-known boost library to serialize them. As we said before, the skeleton instructs the user for his internal behavior, and the user only has to worry about adapting his problem to the interface provided, especially designed for divide and conquer problems. For this, the user must define two objects that will be passed into the main call. First is the info object, that contains information about the structure of the problem. The isBase function returns a boolean that indicates whether or not this is a base case for a given problem. The number of children can be statically defined when creating the object, but if this number is not constant, the user must specify it in the function num_children. The child function receives the child index and the parent problem as a parameter, and must return the corresponding child subproblem. The body object contains information about computing. The base function runs only for base case and returns their solution. The non-base function is optional and allows execution for non-base problems. The pre and prereq function are also optional and allow to do some recomputation before even checking whether it is a base problem or not, which is useful for some divide and conquer problems. The post function performs the reduction. It receives an array of all the sibling subproblem solutions and returns the result of doing the reduction of them. There are different parameters that the user can set to control the behavior of the library. The most important are the following. The first is the chunk size, which defines how many tasks are stolen at the same time for each steal. This value allows stealing several problems at once, which reduces the average overhead per stolen item. However, Using too large values limits the chance of a successful steal, and it can keep some threads idle for longer. The partitioner allows the skeleton to decide when a problem should be processed in parallel or sequentially. The simpler partitioner, which is the default, executes all problems in parallel. The custom partitioner allows the user to implement a custom function that is executed for every problem and decides whether the problem should be processed in parallel or not. This can be useful to reduce the overhead of continually creating tasks when these tasks are very fine-grained. Finally, the behavior flags are a bitmap of flags that inform about the distribution of the input and output problem. For example, we can inform the library that it's necessary to replicate the input problem in all processes, or that the result of solution can be kept distributed among the process, or that the final solution, which is by default only present in process number 0, must be replicated to all processes instead. At last, the polling rate parameter indicates how often the thread should check for a pending MPI word request. This parameter has a great impact in performance, but by default, an automatic dynamic polling rate system is used, which works very well in our tests. This automatic polling rate changes dynamically during execution the value of polling rate, increasing it when no word request is found and decreasing it when word request is found. Now, we will briefly explain the internal workings of the skeleton. We remember that several processes are executed at the same time and they communicate with each other using MPI. Each of the processes has a multiple threads that use C++11 synchronization directives. Each thread has a stack of tasks where the subproblems that are generated are stored. When this stack is empty, the stealing process begins. First, the thread will try to steal work from another thread of the same process. If this is not successful, then it will try to steal work from another process, and so on continually. MPI requests and response are not blocking, allowing useful work to continue while they are not being completed. The system is designed to be highly scalable with a large number of threads and processes, and this is why individual point-to-point requests are used. To increase the performance, a thread can request work for several threads in a single joint API request. All the threads of a process periodically check if there are any pending requests. If so, the thread will try to gather the request work, checking its own stack and also the stack of the other threads in the same process. This work will be sent as a response. The response being able to be partial, if less work than request is found. If there is no work available to be done, the answer will be negative, and the thread that made the request will have to try to steal from another process. Finally, to detect the completion of the algorithm, a well-known colored token system has been implemented, where the token is sent from process to process following a ring scheme. By default, the token color is white, and it means that the algorithm is working and has not yet been complete. Information on the number of requests sent and received by each process is also sent with this token. With this information, a process can detect a termination condition and change the color token from white to pink. This color means that the computation must be complete. It allows pending communications to end, but new requests are not allowed. When all communications are finished, the token turns red, and the algorithm ends definitively. The evaluation of performance and programmability has been performed using 4 parallel applications that present different types of imbalance. QTS, a customizable benchmark with parameters that can generate very unbalanced trees. N-Queens, a program with a certain unbalance that solves the problem of N-Queens. Fib, the recursive implementation of Fibonacci problem sigma at the beginning, which although is not the efficient way to solve the problem, has a very fine-grained subproblem, and it's very useful to visualize the overheads in the parallelization. Finally, top source computes the topological sort of a cyclic direct graph. The level of imbalance of this benchmark is determined by the input problem. In our evaluation, we used one that caused a great imbalance in the execution. We will compare our new implementation with other solutions. One that only uses MPI, another that uses MPI together with OpenMP, and we will also compare it with another skeleton for divide and conquer problems in distributed environments, called the parallel recursion. This skeleton has an API similar to ours, but does not have a dynamic load balancing system, only a static one. Internally, it uses an Intel TBB instead of C++11 threads. It also includes an automatic partitioner that, as we will see, can help it to get a better performance in some benchmarks. The UTS benchmark and Topsort don't have a version that use MPI and OpenMP together, but instead they have a version of pure MPI that implements dynamic balancing mechanism. For the FIB and NQuiz benchmarks, the MPI and MPI with OpenMP versions have an initial static load balancing system. At the OpenMP level, a cutoff mechanism is used to prevent too many tasks from being created, reducing the overhead. This value has been adjusted to the optimum for each test. We use a cluster where each node has a total of 24 cores. The benchmark has been executed for 1, 2, 4, 8, 16, and 32 nodes. For each benchmark, we have tested different combination of number of processes and threads per node and selected the best one. For our library, the best combination is always to choose a single process for each node. Here we can see a table showing the total number of cores used in each test. This will allow you to visualize the performance scaling for each program. QTS is a highly used benchmark known for generating trees in a very significant imbalance. This program supports different types of parameters that allow to build trees of different sizes and shapes. We'll analyze the result for two of them. The first one is a binomial tree that is very difficult to balance and has a great depth, where for each node it's very difficult to know a priori what is the number of its children and also the depth of the branch. This is one of the most important algorithms that we analyze because it presents characteristics that are so important for our development. As we can see, our library achieves very good performance and scalability levels using a sample partitioner for any number of threads. The UTS own implementation using MPI shows good performance until 48 or even 96 cores, but for a large number of cores, the scalability and performance plummet. The executing of parallel recursion is not present in the figure for less than 192 cores, because it failed due to stack overflow caused by large depth of the tree. But even when it does not fail, the performance obtained is very poor. This is a geometric tree with a cyclic branch factor, which makes somewhat difficult to balance its processing, but not so hard as this previous one, and it's not that deep either. The performance of our library is very good, whether we use a sample partitioner or a custom one. With this tree, the deep parallel recursion library does not fail, but neither does it achieve good performance, where it's only competitive when we use only one node. Using MPI implementation is the same as the before benchmark. It achieves good results until reaching a certain number of cores, at which point the performance is degraded. For NQueens, the results are more even, since the level of imbalance is not as great as in the previous benchmark. The deep parallel recursion library achieves very good performance when using an automatic or custom partitioner, and even decent performance with the sample partitioner, thanks to the great complexity of the computations that each problem has. The manual solution that MPI use achieves decent performance and is greatly improved when combined with OpenMP. Our solution always shows high levels of performance and presents the best results when using all 32 nodes. Fibonacci is a challenging and very interesting algorithm for our library due to the extremely small granularity of its problems. Most functions consist of just one operation. The overhead caused for the internal treatment of the stack will be very noticeable. Analyzing the results, we see that the performance achieved with the sample partitioner is not very good, and the overhead caused by the handling of the stack is notable. Although it's interesting to know the difference with the parallel recursion, where with a sample partitioner, the performance is much worse. For the parallel stack recursion, it's necessary to use a custom partitioner to achieve good performance, which greatly improves the performance. For the parallel recursion, we get decent results with the use of the automatic partitioner, and even better if we also use a custom partitioner, although not as good as the ones achieved with the new implementation. Manual implementation using MPI performs well up to 384 cores, at which points performance parameters. As expected, the use of MPI combined with OpenMP improves this and allows it to compete with our solution, matching the performance even when we use 768 cores. In the top source benchmark, our skeleton shows very good levels of performance and scalability, and the rest of the solutions are quite far away. Deep parallel recursion, as expected, does not perform well in this unbalanced benchmark as it lacks a dynamic load balancing system. The solution that use only MPI use a framework developed in C called MTS that includes a dynamic load balancing system. And although it achieves a certain level of performance, it's quite far away from the performance achieved by our library. We use several commonly used metrics that allow users to measure approximately the programmability levels of the different implementations. Slog, as known as the number of lines of code, the cyclomatic number, and the hasted effort. The level of programmability is shown in the following charts, showing the relative value of the parallel versions compared to the values of the sequential versions. The differences between deep parallel start recursion and deep parallel recursion are not very relevant since they use a very similar interface. The big difference is with respect to MPI and MPI with OpenMP, where the user must write more personalized code to achieve good performance. In this case, the more complex the parallelization is, the level of effort necessary to implement it grows drastically. Being relatively simple for simple parallelizations, but becoming much more complicated the more techniques the programmer wants to use, such as the creation or synchronization of tasks, load balancing, etc. Something that our library does automatically. This is the big difference in programmability. Finally, our conclusion. The current paradigm of distributed computing focuses on combining parallel programming models for shared and distributed memory to achieve good efficiency. Divide and conquer is a very important pattern of parallelism that appears in many problems and can be used to implement other very relevant patterns. We present a highly optimized skeleton called deep parallel stack recursion that allows the automatic and efficient process of divide and conquer problems on multi-core clusters. The implementation is especially designed to work properly with problems with large levels of recursion and or high degree of imbalance. The new proposal hides for the user all the complexity of distributing and processing tasks, offering a simple API for the user to implement their problem. It achieves very good performance and programmability results in the evaluation benchmarks used. Thank you all for your attention.